So we solved this heat equation on the entire real line last time. You know, the thing to observe here is x here is going between minus infinity and infinity. We don't have a traditional boundary condition. And we have this sort of additional requirement on the initial condition. Because we are going to be integrating from minus infinity to infinity, you know, we require the functions that we're integrating be well behaved in these infinite intervals. So as always, we started with traditional separation of variables, and we separated the equation into a t-domain problem and an x-domain problem. Here, be careful here, we set it equal to just lambda, not negative lambda. The negative lambda was nice because in our series solution, you could kind of visually see that there is a decaying exponential term. But here, it'll be an integral, so it's not necessary to write it that way. There's no advantage, really. And so we get our two problems, the x-domain problem and our g equation. And we check the cases for non-trivial solutions. So if lambda equals 0, we have a non-trivial solution. Because of the boundedness, we have to make the coefficient a equal to 0. And then for the lambda less than 0 case, we see that there are viable solutions. For the lambda less than 0 case, we end up with this basis. And so this becomes our general solution for the F equation in the lambda less than 0 case. And so the thing I just want to really emphasize, and I mentioned this last time, is these functions, you should really, you know, they're complex functions. You know, we're so used to looking at real exponential functions, and we all know that a real exponential function is unbounded. But these are not, these are complex exponential functions. So they're actually, you know, very well behaved. They're oscillating functions. So here, these are bounded functions that are oscillating. Remember, e to the I mx is really, if we use Euler's formula, this is really cosine mx plus I sine mx, you know. So that's something to just keep in mind here. And so once we solve the F equation, then we solve the G equation. Then using superposition, we put the two together. So I have my, you know, F equation solution, and then G equation, and we get our superposition solution that, you know, once we find the coefficients, should also satisfy the initial condition. Remember, our product solution satisfies the PDE and boundary conditions, but not the initial condition. So we need the entire thing to get the initial condition. So one last little extra manipulation here is we can actually write this second integral that we get, because we're going from minus infinity to infinity by symmetry and integral trickery. We can just write the solution as a single integral. And this, you know, to me looks a lot like the regular heat equation solution. You've got your sum, you've got the coefficient, you've got your oscillating term, and we've got our decaying exponential term. And then finally, when we apply the initial condition, we end up with, you know, a Fourier and inverse transform here. And so we can solve for the coefficient here. We conclude that the A sub m coefficient is u hat of m, the Fourier transform of u, what we're calling the Fourier transform of u. So at the end of the day, here's the solution to that heat equation on the entire real line, you know, summarized in a neat little mathematical box. So, you know, I think it's really important to try and see it for what it is beyond just the formulas. So, you know, especially to relate it back to, whoops, what happened there? especially to relate it back to the Fourier series. So in particular, what do I mean? Here I see a sum, just like a Fourier series. Here's the coefficient. We call that the Fourier transform. That's basically the coefficient. That's the Fourier coefficient. And then we've got our cosine and sine term. Then we've got our decaying exponential term. And here, here for this Fourier transform, the Fourier coefficient, I hope you see exactly essentially a projection formula. We're taking the given data, we're doing an inner product against the basis element, and then somehow normalizing with the dividing by 2 pi. So that's the coefficient, that's the Fourier series, but now it's in this continuous version with an integral. And so we can show that if the data we're giving, the heat equation is well behaved, is absolutely integrable, then the transform, the Fourier coefficient, will be bounded. So here, there's no tricky math here. It looks a little weird, but you should just work through it. The only thing I add, the only thing that's different here is this is not a traditional exponential function, that it's bounded. And so we can bound the whole thing. So there's a more general result here on these transforms, these Fourier coefficients. Because, if you think back to our regular Fourier series theory, the convergence was about what were the coefficients doing. And so here we're also concerned that these coefficients are well defined. In this case, functions. In the Fourier series case, they were just a sequence of numbers. So here, the Riemann-Lebesgue lemma. So the Riemann-Lebesgue lemma is, a sub-result of the Riemann-Lebesgue theorem, which is a bigger result in complex analysis, which I won't go to. But so this is the Riemann-Lebesgue lemma, and it has to do with the convergence of these types of integrals and stuff like that. So here, the Riemann-Lebesgue lemma says if u of x, our initial condition, is absolutely integrable, then u hat of m, the Fourier coefficient generated by u of x, will be bounded, which is good. We don't want these things going up to infinity. So there's a claim that u hat of m is continuous. So that's nice for something that we're putting in an integral. And finally, that u hat of m goes to 0 as m goes to plus minus infinity. This kind of has to do with, if you look at this integral, because it is an improper integral, we do need to kind of address, okay, what's going on, with that part. Well, I guess the improper part here, this is in terms of x. So I really mean in terms of m here, because it's valid for all reals. So we just want to see what's the asymptotic behavior? That's the right word to use, the asymptotic behavior of the function. So we have all these nice results, and I won't prove the full version of it, but I will prove each of these results. And as I said, that the Fourier transform of the data will be well behaved if our data coming in is integrable, relatively well behaved. And this result is the same result we had before, where we talked about the oscillatory integral cancellation. So here, if you think of this as more like cosine and sine, you can kind of think when you multiply the function against it, just for an easy picture in your mind, you have a positive function that you're multiplying to cosine or sine, and you'll have the function will dip above and below the x-axis. And so as m goes to infinity, the frequency m here, that's the frequency of our wave. It's e to the I mx equals cosine mx plus, or here minus I sine mx. So as the frequency increases, we get all these tiny little waves, and the overlap, the area above and the area below, according to this theorem, are canceling out and going to 0. And this is what we'd call the oscillatory integral cancellation. We've seen this phenomenon earlier. And also, from a numerical analysis, more practical point of view, this will also say for large M, just truncating it should be okay, because at the ends, it seems to be going to 0. At the tail, it seems to be going to 0 for large M. So if we cut it off at minus M to M, minus capital M to capital M, that should be okay. We should be able to get, a good representation of the original data still. So item number 1 was proved earlier. So for proof for item number 2, let me preface this. If I just dive into the proof, it's a little random. So for item number 2, so just from an analysis point of view, there's, so there's a general question that we ask in analysis is, if I have a sequence of functions, so here's fn of x, and this converges to some function f of x. This is as n goes to infinity. Okay. The question is now, so I'm going to do an implication arrow and put a question mark next to it. The question is, when can we conclude that the integral of the sequence of functions will converge to the integral of f of x? So it's not always true. It's, knowing, because this is analysis, here's how everything works in analysis. It's probably true most of the time, but there are a couple of little, counterexamples where it doesn't work. So it's not true always. And so then we have to have theory, and someone has to do a proof, and we have to have a class about it. So the question is, if you have a sequence of converging functions, when is it okay to also just be able to slap on integrals and conclude that the integral of the sequence of converging functions converges to the integral of the function that the sequence of functions converges to? So there's a theorem in analysis called the dominated convergence theorem. So yeah, we're going to use dominated convergence, but I think, yeah, that's essentially it. So I think that'll give us some type of uniform convergence. So here we're going to use this theorem from real analysis called the Lebesgue dominated convergence theorem. And so, if you haven't seen this theorem, don't worry about it. I just didn't want to give you the Riemann-Lebesgue lemma without giving you some type of proof. Okay, so if you haven't seen this theorem in action, here's a nice example of when we would use Lebesgue dominated convergence theorem. So for continuity, remember continuity is a limit definition. We can conclude, in Calc 1, we say f of x is continuous at x equal to a if the limit of f of x as x approaches a equals f of a. And so that's what we're doing here. Here, I'm going to pick any real number m, and then pick any sequence of real numbers m sub n that converges to m. If I can now show the limit of u hat of m sub n as m sub n goes to m equals u of m, basically in the limit, what you should see is we've just basically we've taken m sub n and applied the limit in here. And that's really what continuity says. Basically, the continuity allows us to bring the limit inside. So here, if we can show this limit's true for any m, and sequence m sub n that converges to m, then that'll imply that our transform's continuous. So now here's the part where you kind of have to be careful and remember the definition. The definition here of u hat of m, this is actually an integral. This is an integral from minus infinity to infinity, u of x e to the minus I mx dm. So when we're talking about this limit, which we don't know is true, all right, so I want to put a question mark right here. This is what we would like to show. When we're talking about this limit, we're talking about a limit of a sequence of integrals. Evan?
So essentially, this is a question of whether or not we can interchange the limit as mn approaches n and the integral, which is another limiting process, right?
Right. And okay. Uniform convergence certainly will allow us to do that.
Okay.
And I think that's how the dominated convergence theorem is proved. But yeah, that's exactly the question. When can we just interchange the limit and the integral? That's exactly the question here. That's exactly the question here. So now, I start talking about this function. Say, hey, I say for each real number m sub n, define u sub n of x to be ux times either I minus mn. So you think, well, this seems random. Where'd this come from? So remember, if you integrate this, that gives us the transform. So it's not entirely random. If you go back and remember that this transform here, this is actually an integral. Okay, so here I'm defining a sequence of functions u sub n. And what we know about u sub n is that this is a continuous function. So here, if I send n to infinity, the m sub n here, we can replace with an m. So and also we should note each of these u sub n of x is the absolute value is less than absolute value of u of x. Okay, so this all seems random, but this is exactly the condition we need. This is the, when we talk about the dominated convergence theorem, this is the domination part. So this is what we want, that each term of the sequence is being dominated here. And so what we can conclude by the theorem is that the limit of the integral will be true. You can slap on the integrals here, that the limit of the sequence of functions converging to a function here, in this case, because of this Lebesgue dominated convergence theorem, allows us to conclude that if the sequence of functions is converging, then the integral of the sequence of functions is also converging. And so that's, so the big thing you should see is we just slapped on integrals. From here to here, the big development is we slapped on integrals. And it's this, just a general, you grab a person off the street would say, well, why wouldn't you be able to slap on integrals? And that's not how math works, right? We don't assume the thing that we want to be true is true. That's too easy. So here, we ask the other question. Just because a sequence of functions does converge, why would you assume the integral of the sequence of functions converges, right? That's the right question to ask in analysis. Not why not, but why would it do that? And then we have to prove it, right? That's the whole point of analysis, right? So here, with the Lebesgue dominated convergence theorem, we can conclude that this sequence of functions converging allows us to also conclude that the integral of the sequences of functions will converge. And if you unwrap this notation, this statement here is exactly the same as this continuity statement I'm trying to prove. It's really important to keep in mind that when we're talking about u hat of m, if you unwrap the notation, u hat, this is really an integral, right? It's the integral, it's the integral of this expression, which I'm now calling u sub n. So anyway, I wouldn't worry about this slide too much. Those of you taking analysis or that will take analysis, watch out for the old, so we got the two big theorems as the monotone convergence theorem and the dominated convergence theorem. And so these are like the two big theorems in this part of analysis, which always show up, which you're always asked about for those of you in analysis. But here for us, I just wanted to show this result to you, just to give you some kind of proof, but certainly we shouldn't worry about the analysis of it. Here's the last part, which I think is kind of a neat, very easy proof. And this is a result that follows from the theorem, but I want to prove it for a very simple case where we're going to look at indicator functions. So for those of you doing analysis, we always solve things in baby steps. You start with indicator functions and then you build up, and then you create a function that's the positive part and the negative part, and then you create the function. So this is we're starting, we want to prove the result, which is the oscillatory cancellation in the integral for the indicator function. So here I'm going to define, here's the indicator function. It's also known as sometimes as a characteristic function. So here, if our input is inside the domain, then the function is equal to 1. if our input is not in the domain, minus L to L, then it's 0. Okay, so it's a very simple function. It's like a little step function. 0 everywhere except between minus L to L, it's 1. So this would be what's known as an indicator function for this set negative L to L. You can define this in general for any set. So instead of minus L to L here, we could have any set A in here. And then this would be an indicator function for whether we're in the set A or not. And typically in analysis, they might write this as chi sub A of X. And that would be an indicator function for whether the function is in the set A or not. And it's a very common function used in analysis. You know, it's a fundamental function that you can build all other functions out of. So here, what I want to prove, so remember the result we're trying to prove is this integral as m goes to infinity, this integral here, as m goes to infinity, that integral goes to 0. I want to show oscillatory integral cancellation. Okay. So I'm going to do a squeeze theorem. Remember when you studied squeeze theorem, you said, when am I ever going to use squeeze theorem? All right, so here, let's use squeeze theorem. So first, I'm looking at the absolute value here of this is u hat of m. OMG, maybe I should give up the writing thing. That's our transform u hat of m. And so here, this is equal to, why is it equal to that? Oh, so here, because of the indicator function. So here, remember, it's 0 outside of this interval. And it's 1 inside the interval. So you should imagine there's a 1 written here, which is this one right here. Yes, indicator functions made life so easy. And so now we just integrate e to the u in the usual way. And then I evaluate it from minus L to L. And so I get this. This is just the usual integral of e to the u over u. And then I use a triangle inequality, and I multiply top and bottom by I here. So there's an I down here. So here this is a modulus, you know. So, and then I use triangle inequality upstairs. And now these are oscillating functions. These are not traditional exponential functions. That's like I times quantity cosine ml plus I sine ml. And this is like I times quantity cosine ml minus I sine ml. They're both bounded functions. They're just cosine and sine. They're each bounded by 1. So I bound the whole thing by 2 over m. And so now if you look at the ends, we've concluded that this thing is less than or equal to 2 over m. So I can set up an inequality. So I know if the absolute value of A is less than B, then we know A is between, negative B and plus B. So here's negative B plus B, and here's that A term. Here's your absolute value of A is less than or equal to B. I put those on either side, just rewriting the absolute value. So now you send m to infinity, the limits on the left and right side both decay to 0, this limit and this limit. And so, the integral in the middle goes to 0, but the integral is exactly our transform. If you want to look at it in the integral version, here we get our oscillatory cancellation. And that's the proof of the case. That's the proof in the case where we have, the indicator function. Complex hyperbolic functions. I'm sure a lot of this is, so Jeff asks about the hyperbolic functions. I'm sure a lot of this is also done in hyperbolics because that's a very common kind of way of analyzing this, rewriting everything in a hyperbolic form. So I'm sure there's something to do with that. Yeah, I don't necessarily know too much about that. I have some experience with it. So I want to talk about the asymptotics here. What happens to u of xt, because this is the solution of the heat equation on a quote unquote infinite rod. So we want to know what happens to u of xt as t goes to infinity, and to try and have some kind of asymptotic analysis, So I have to remind you of a result from Calc 3. I don't think we did this on a homework. Sometimes I make y'all do it on the first homework, but I don't think I made you do it on this one. So here, if you look at the integral that we're working with, that's the solution of the heat equation. It involves the integral of, so let me show you here. Look, it involves the integral of, right here. I want to know, what does this function do for large t? And here, there's this type of exponential here with a square, because this integral is in dm. And look, this m is being squared. So the generic form here has to do, we first want to talk about how do you integrate something that's e to the minus variable squared. Okay, and that's a very common problem that's done in Calc 3. I don't know if you remember this problem from Calc 3. So it's like, this is one of those problems it's good to remember the trick. So Calc 3 problem is, how do you do this integral? You can't do a simple u sub. There's no x's downstairs. So it's kind of a complicated problem. So I don't know if you remember the trick. The trick is to square the integral and use Fubini's theorem. So I square the integral. So just put parentheses around it, square it, and then break up the square. I write this as the integral times itself, but I changed the dummy variable on the second integral. Here, nothing has changed except I squared it, and then I wrote it as the integral times itself. And in the second integral, I changed the dummy integral from x to y. Okay, now here comes the trickery. Using Fubini's theorem, we can write this, listen to these words now, this product of these single integrals as a single iterated integral. And so this thing is known as a double integral or an iterated integral. And so that here we took these two single integrals, and through Fubini's theorem, which I'll let you review, we're able to combine them into a double integral, what's called an iterated integral. In this case, it's easy to do because the integrals are, they're essentially in two different variables. There's no real overlap here. And so then once we get them in this form, the trick is to now use polar coordinates. And again, if you want to review this stuff, that's great, but this class isn't about using polar coordinates to solve this integral. So I wouldn't, be too concerned about it. When we use polar coordinates, I don't know if you remember, but because of the Jacobian, this dx dy gets replaced with an r dr d theta. Remember the Jacobian? And the x squared plus y squared gets replaced with an r. Now here, e to the minus r squared r dr, this we can integrate using an easy u substitution. And so this is one of those tricks you'll see every once in a while. Someone will try and trick you and ask you, oh, how do you integrate this? And you just go, oh, square the integral, of course. That's always the right answer. Don't forget the of course. So once we integrate it, we can show, so now this is a really easy integral. You can just pull the integral apart and integrate each part. We can show the integral, it integrates to pi. And so now the question is, how does this have anything to do with what we're talking about? So now if you go back to our solution of the heat equation here, that's got this Cauchy principal value thing. Here, this is an integral in dm, and it's got this e to the minus m squared kt. So that's kind of generically just like this. You got a dx and then e to the minus variable squared. So we can bound this part. That was the very first property of the Riemann-Lebesgue lemma, told us u hat of m was bounded by m over 2 pi. E to the imx, remember this is actually cosine plus sine. This we can bound with 1. So the only term that's left is this e to the minus m squared kt stuff. And, you know, using the above tricks, you can rewrite it so that the entire thing is being squared. And then you can use like a u substitution, and we can take advantage of this result. You know, you don't have to repeat this entire procedure, but that's basically what you can do. And we can solve the integral and show that we can bound our solution by this expression. And so now we can send t to infinity and see what happens as t goes to infinity. We see our temperature goes to 0 as t goes to infinity. So that's the asymptotic behavior. You know, we want to know what's happening, you know, to this equilibrium essentially for large t, you know, for this infinite rod, because that's not normal, folks. The infinite rod's weird, right? So here's just to show you the technique we use to figure out what it's doing for the large time behavior of the function. So one other thing I want to talk about, and then we'll discuss this heat equation in a more general setting, is for how do we do large time estimates? With our Fourier series, each term was decaying because of the exponential term, but we knew the first term would be the slowest decaying. In this case, because m goes from minus infinity to infinity, you know, in our Fourier series, we had discrete eigenvalues, and we had m going from, you know, 1 to infinity. Here, because m is going from minus infinity to infinity, there's no smallest Fourier mode per se. So here we actually do something that's very, you know, Calc 2-ish. We just do a Taylor series expansion of u hat of m, or Maclaurin series. So everyone, you remember your Maclaurin series from Calc 2. So we come back all the way to Maclaurin series, and we basically just want to, you know, do an expansion. Okay, so here, we do some math tricks. We can rewrite this doing some math trickery, and you know, if you want to go through the painful completing the square, you know, I'll let you do it. Here, if you square this out and do all the math, you should end up back with this. So we're going to rewrite this. We're going to replace the u hat of m with this one term approximation, and then do this completing the square and calculate this integral here. So here now this integral looks like the kind of integral we saw before, where it's e to the something squared, e to the minus something squared dm. It's not quite the same, where you'd have to use a little u sub to actually completely do the integral, but this has that same form. And so you can show this integral integrates to root pi over root kt. So here's our u of xt, where we approximated u hat with the first term of the Maclaurin series. Why not use more than one term? Certainly you can. You know, this is just a starting point. If we use more than one term, to do that second integral, we're going to need to do, oh, that second integral will actually be easy. Yeah, so, but we certainly can. And so now we have this approximation now. And here, you know, there's something interesting to observe, that if we move this kt over to the other side, we get square root of kt times u of xt looks like this function. And if you graph this shape, this turns out to be a bell curve. So it's like this bell curve, you know, diffusing in time, and we're dividing by kt, and t is going to infinity. So there's kind of this bell curve lurking in the background here of the solution of this infinite rod problem for the heat equation. There's this kind of, you know, bell curve lurking around somewhere. So yeah, for each fixed t, square root of kt times u of xt has a bell shape. It's this kind of scaled bell shaped. I don't know if this is supposed to say from almost all initial data. But yeah, so the bell curve thing is not a coincidence. So here it turns out there's this thing called the fundamental solution of the heat equation. And that has to do with the bell curve, the Gaussian kernel, however you want to think about it. And so if we have the heat equation on an infinite rod where the initial condition is a Dirac delta function, then we can show this fundamental solution will look exactly like the Gaussian kernel, the Gaussian bell-shaped function. So here, the Dirac delta function is kind of a weird function. It's thought of as this concentrated pulse function. So at a single point, we're putting this, you know, infinite amount of energy or whatever at a single point. Outside of that point, there's nothing, it's zero. So I'm sure some of you have perhaps seen the Dirac delta function. So it's kind of defined almost formally. You know, they just write down the equations and go, this is how we're defining it. Does it mathematically make sense? We don't really even know. So it's defined formally this way. And so here, you can see here, when x equals c, this thing you'll have delta of 0. And at 0, we define the Dirac delta to be this infinite impulse. So when x is not equal to c, this is always 0. When x equal to c, this is equal to infinity. And you can see the result of the integral is f of c. So the way I think of it is like if you have a metal plate, we're hitting one part of the metal plate really hard with a lot of force, and it forces the metal plate in that one section to stick up. And this is the point f of c. And this is the part where we hit the metal plate really hard at one point. It's kind of a punch function, you know. So that's what I see when I look at this, that when x equals c, it punches the function. Here, when you see f of c, you should kind of see like f of c maybe, I don't know, times 1. You should kind of see like a height times a width type thing happening, because it is an integral. Anywho, you know, I'll let you think about the Dirac delta function. This is a very common special function in all of science, not just here, you know. And here, if we pick f of x up here to be 1, the constant function 1, and choose c to be 0, so center it at the origin, then we get this integral is true. So, you know, they always kind of draw the delta function like this, where you, and then as you get closer and closer, and then the limit is this, it just blows up to infinity, this kind of spike. So yeah, this is, as I said, it's formally defined. It's not, this is a very weird function to define, okay? So, okay, if you accept the Dirac delta function, this weird infinity pulse function at a single point that has this property in general and this property. So that's just by definition. And now, okay, here's the whole point. What does this have anything to do with PDEs? If we now look at this heat equation problem on the infinite rod where the initial condition is the delta function, where C, so at the center of the rod, okay, so I've got this infinite rod. So let me draw, here's this infinite rod, goes forever. This is the center of the rod. We superheat the center of the rod, you know, we superheat the center of the rod and then step back and ask ourselves, what does the temperature profile look like when we've superheated the center of the rod and now let time move forward? This thing starts to take, as time goes forward, we see our traditional Gaussian bell shape from probability theory. So we can show the solution as we've derived would have this form, where here this would be the Fourier transform of the initial condition or initial data, which is that delta function. And so I won't do the math, but we can show that, you know, you can rewrite it and do, you know, put in the definitions. And here I've introduced a dummy variable. So what's the X bar here? I've introduced a different dummy variable because I don't want to use X in two different contexts here because I already have X. And we already used Y, you know, so anyway, so here you can show that it integrates to this function here. And this function, you know, looks a lot like the Gaussian kernel that we find in probability theory. And so it's amazing, you know, for us to be sitting here doing PDEs, but then we find this function from probability theory showing up here, you know. So all these things are connected somehow, you know. The solution of the heat equation on an infinite rod is related to this bell curve, you know, and the bell curve, of course, you know, in statistics, the central limit theorem, how important the bell curve is. Evan.
So the idea with the with the Green's function method of solving PDEs is we take sort of an integral over all of these fundamental solutions to kind of construct whatever initial condition we want.
Right, exactly. It's kind of like these are now basis functions themselves, right? There's somehow form a basis for boundary conditions. So yeah, let me just wrap up, I guess, with this slide here. The other couple of slides, you know, so one question now is, how does our solution to the finite rod problem, how does that relate to this fundamental solution to the infinite rod? And so I want to use method of images next time on Monday to solve the finite rod problem with the infinite rod solution. And then you say, well, how does the infinite, well, how does this solution here? So now you're solving the finite rod problem, you know, with the infinite solution. How does the infinite solution match up with our series solution? And it turns out they're the same. So if you try and now find the Fourier series of this solution, you end up getting our usual Fourier series solution. So I'll talk about all this stuff on Monday, and it's nothing you should really worry about right now. And you can read ahead if you want, but don't worry about it for right now. So yeah, let me just stop here with this final slide here where it talks about the fundamental source solution and the connection to the bell curve. So the material on the Fourier transform will not be on the test. I want to repeat that. I also want to mention that if you look at the formula sheet, there are some Fourier transform formulas on the formula sheet, but the formula sheet is old. So don't worry about the Fourier transform for the test. The test will focus on wave equation, heat equation, and make sure, wave equation, Laplace's equation, and make sure you know D'Alembert's solution, okay, to the wave equation. Yeah, so don't worry about Fourier transform, please. You know, that's too much. So yeah, so so basically we get this, if you have this initial concentrated heat source at the center, as time moves forward, we get this bell-shaped curve. And I graphed it for, various choices of t here, and I just picked some value of k to graph this fundamental solution. And you can see, I guess, at time t equal to 0 or something, there's this infinite impulse, this spike right at the center. And then as time moves forward, that spike starts to, decay. And as I said, this same curve, comes up in statistics. And you can talk about random diffusion and motivate the whole statistical derivation using probability theory, which I'm not going to go into, but this is a really fascinating connection. This is, because I always like probability, I always like PDEs, and then so to find this connection, it's just it's very exciting, to see this, to be able to characterize solutions of PDEs with the Gaussian kernel using a probabilistic sense. We're able to characterize solutions of PDEs. So all right, folks, I'm going to stop right here. Thursday we have the test. The focus of the test is, as I said, wave equation and Laplace's equation. Make sure you know D'Alembert's solution. Don't worry about the transform for the test. We'll continue this on Monday. Okay. All right, everybody, I'm going to stop right here.